All right, so we got this request to dive into a paper about something called jet substructure.
Huh.
And, I got to be honest, at first glance, I was like, jet substructure. That sounds kind of technical,
Yeah, it's not exactly the catchiest term.
right? But, we dug in a bit, and
It's actually way cooler than it sounds.
yeah, it's actually pretty fascinating stuff once you get past the jargon.
Exactly.
So for our listeners who, like me, might not be totally fluent in particle physics lingo.
Can you give us like the elevator pitch? What is jet substructure in a nutshell?
Okay, so imagine trying to figure out who threw a giant party, but you weren't there to see it. All you have are the remnants, the aftermath, you know, scattered confetti, half-eaten snacks, stray party favors. Jet substructure is kind of like that, but on a subatomic level. We're trying to reconstruct the events of a particle collision by analyzing the patterns in the particles that come spraying out.
Okay, so instead of a party, we're talking about like a subatomic collision. And those jets are like the confetti left behind. Exactly. In particle physics, we have these things called jets. They're like showers of particles produced in these really high-energy collisions, like at the Large Hadron Collider.
So instead of a party, we're talking about a subatomic collision. And those jets are like the confetti left behind.
Exactly. And just like you might look at the type of confetti or decorations to guess who threw the party, physicists try to figure out what kind of particles created those jets.
So are we talking about like different kinds of confetti then? What makes one jet different from another?
Great question. So jets can be formed by different fundamental particles, like quarks and gluons. These are like some of the most basic building blocks of matter, right?
Okay, so quarks and gluons are like our guests at this particle party. But why do we care who the host was? What's so important about knowing if a jet came from a quark or a gluon?
Well, understanding where these jets come from, it helps us unlock these like deeper secrets of the universe. It's like putting together a puzzle. The more pieces we have, the clearer that bigger picture becomes.
So this paper we're diving into today, towards an understanding of the correlations in jet substructure, it's all about analyzing these particle showers.
Precisely. And it's not just any paper, actually. It's a report from a whole conference. Boost 2013, it's called. That's where, like, all these physicists get together to share their latest and greatest findings about jet analysis.
A whole conference dedicated to jets. Sounds intense. What kind of things would they even be discussing?
Oh, all sorts of incredibly clever techniques they use to like analyze these jets, like grooming and tagging.
Grooming, like we're giving the particles a makeover.
Well, kind of.
Yeah.
Imagine you're trying to have a conversation at a really loud party, right? It's hard to hear anything over all the noise.
Yeah, you probably want to find a quieter corner.
Exactly. These grooming techniques are like finding that quiet corner, but for particle data. They help to like remove the unwanted noise from the jet data so we can get a clearer picture of what's really going on.
So it's like filtering out the unimportant stuff, kind of like tidying up after that party so we can focus on the key details. What kind of noise are we even talking about here?
Think of it as separating the main party guests from like the random people who just wandered in off the street. In particle physics, this noise comes from something we call soft radiation. Basically, these are particles with like really low energy that can clutter up the data.
Okay, so we need to tidy up a bit before we can really understand what's happening. But how do physicists actually groom these jets? What's involved in that process?
There are actually several different grooming techniques, each with its own way of cleaning up the data. One pretty common technique is called trimming.
Trimming, like we're giving the jet a haircut.
Haha, yeah, kind of. Trimming removes the, let's say, the softest parts of the jet, the parts with the lowest energy. It's like trimming away the stray strands of hair to get a cleaner, more defined look.
So trimming helps us focus on the higher energy particles in the jet, the ones that are more likely to tell us something important. Are there other techniques like this?
Yeah, there's also pruning, which, well, it removes the least energetic subjects within the jet. So imagine you're looking at a tree, right, with lots of branches, and you want to focus on the sturdiest, most significant branches. Pruning helps us do that with our jets.
Interesting. So we've got trimming for a clean cut and pruning for highlighting those major branches. What other grooming techniques are out there?
Another really important one is called soft drop. This one's a bit more complex to explain, but essentially it focuses on the most energetic parts of the jet and, well, it discards any softer subjects that are too far apart. It's kind of like looking for the main cluster of party guests and ignoring anyone who wandered too far away from the action, you know?
Okay, so we've got these jets all cleaned up with these filters, like
Yeah.
we've tidied up after the party.
Exactly.
Now what? What do we actually do with these nicely groomed jets?
Now comes the really interesting part, analyzing them.
Yeah.
So we use something called observable classes, which I know might sound a little intimidating.
It does sound kind of technical.
Yeah,
Yeah.
but it's actually a pretty intuitive concept.
Okay, break it down for me.
All right, so
What are observable classes in the context of these particle jets?
okay, well, think about it like this.
Well.
You're at that party we were talking about
Yeah.
before, right? Trying to figure out who the host was.
Right.
You might look at the decorations,
Mm.
listen to the music,
Yep.
maybe even like peek at the snacks in the kitchen to see what kind of food they've got laid out.
Right. Different clues can give you different pieces of information.
Exactly. Each one of those things you just mentioned, the decorations, the music, the snacks, they're all like an observable class in the scenario.
Okay.
They each give you a different perspective on the party and help you like narrow down who the host might be.
So in our particle jets, these observable classes are like different ways of measuring or analyzing the jet to try to figure out its origin.
You got it. So the paper we're looking at, it talks about a bunch of different observables,
Right.
or like measurements you can make about a jet.
Okay.
Like how many particles are in it, how the energy is distributed within the jet, even how clumpy it is, meaning how closely packed the particles are.
So it's like we're looking for patterns in the confetti, seeing if it's spread out evenly or clustered together in certain areas.
Exactly. And just like some clues are more helpful than others in figuring out who threw the party, some of these observable classes are better at distinguishing between quark jets and gluon jets.
Right.
That's really what we're trying to do here.
So the paper spends a lot of time on one specific observable called unconstants,
Yes.
which I gotta admit sounds a little intimidating.
I know it's a mouthful,
It's a mouthful.
but it's actually simpler than it sounds.
Okay.
And constants is just shorthand for the number of particles in a jet.
Okay. So we're literally just counting particles.
Pretty much.
Okay.
But that number can tell us a lot.
Okay, so why is the number of particles so important? What does that tell us about whether the jet came from a quark or a gluon?
Well, remember how we were saying that quarks and gluons are like the guests at our particle party?
Right.
Well, it turns out they have different characteristics.
Okay.
And one key difference is something called color charge.
Color charge. Like, are quarks red and gluons blue?
Not quite. It's not actual color.
Okay.
It's just a way of describing how quarks and gluons interact with the strong force, which is one of the fundamental forces of nature.
Okay.
It's a little complicated, but basically quarks and gluons carry different amounts of this color charge.
Okay.
And that difference, it affects how many particles they produce when they create a jet.
So a quark with a certain color charge might throw a smaller party,
Right.
leading to fewer particles in the jet, while a gluon might throw a wilder party with more particles.
It's a great way to put it. And because of this difference in color charge, quark jets tend to have fewer particles than gluon jets.
Okay.
On average, of course.
So just counting the number of particles in a jet can give us a clue about whether it came from a quark or a gluon.
Exactly. It might seem like a really simple observation, but it can be incredibly powerful for physicists who are trying to unravel the mysteries of these particles.
So then why bother with all the other observables? If counting particles is so effective, why not just stop there?
Well, it's true that inconstants is a very useful observable,
Yeah.
but it's not perfect.
Okay.
And sometimes it can be tricky to get a completely accurate count of the particles in a jet.
It's like trying to count the confetti when the wind's blowing it all over the place.
Exactly. There's always a chance for some error or uncertainty.
Right.
And that's where those other observable classes come in.
Okay.
By combining inconstants with other measurements, we can significantly improve the accuracy of our identification.
It's like finding that one extra clue that cracks the case wide open.
Precisely. It's all about getting different perspectives, just like we were talking about with the party.
Right.
If you only look at the snacks, you might miss a crucial clue that's hidden in the music selection.
So it's not just about having more information, but having different kinds of information.
Exactly. And this is where the concept of orthogonal information comes in clues that provide independent confirmation, like having multiple witnesses who saw different angles of a crime.
It's like having a puzzle piece that only fits in one spot.
Exactly. And when you find that perfect fit, you know you're on the right track.
So this paper, it actually dives into how different combinations of these observables perform in distinguishing quark jets from gluon jets, right?
Yeah, they ran a bunch of simulations and tested out different combinations to see what worked best.
And like good physicists, they put all this data into some nice, easy-to-read graphs for us.
Of course, because what's the point of all this research if you can't visualize it with a good graph?
Exactly. So we're looking at figures 3, 5 letter, and 8, specifically in the paper. Can you walk us through what we're seeing here and what makes these graphs so important?
Absolutely. Now, these graphs might seem a little intimidating at first glance.
They do have a lot going on.
Yeah, there are lines and colors and axes galore,
Hmm.
but they're actually telling a fascinating story.
Okay. I'm intrigued. Tell me more.
So basically, these graphs are showing us how well different combinations of observables can separate quark jets from gluon jets.
Okay.
Think of it like a scorecard for our detective work.
Okay, so the higher the score on the graph, the better that particular combination of clues is at solving the mystery of the jet's origin.
Exactly. The graphs are plotting something called efficiency, which basically means how often we correctly identify a quark jet as a quark jet and a gluon jet as a gluon jet.
Gotcha.
So the higher the curve on the graph, the better that combination of observables is at making those distinctions.
So we're looking for the combinations that create the highest curves, the ones that give us the most bang for our buck in terms of accuracy.
You got it. And what's really remarkable is that by combining just a few key observables,
Okay.
we can achieve incredibly high levels of accuracy in distinguishing these jets.
Wow. It really is amazing how these tiny particles, these jets, can hold so much information about the fundamental nature of the universe.
It really is. And it's not just about quarks and gluons either.
Oh, there's more.
Yeah. This paper also dives into identifying even heavier particles, W bosons and top quarks.
Okay, let's talk about these heavier particles.
Mhm.
Why are they important and how do they fit into this whole jet substructure puzzle?
Well, imagine these heavier particles as the VIP guests at our particle party.
Okay.
They're not just any guests, they're crucial for understanding the fundamental laws of physics.
Okay, I'm intrigued.
Yeah.
Tell me more about these VIP particles.
So W bosons and top quarks, they're like, the celebrities of the particle physics world.
Okay.
They're way heavier than quarks and gluons. And they play this crucial role in something we call the standard model.
The standard model. Is that like the guest list for our ultimate physics party?
It's more like the laws of physics that govern who even gets invited to the party in the first place. The standard model, it's basically the framework that describes all the fundamental particles and forces in the universe.
Wow, that's a pretty big deal.
Ooh.
So these W bosons and top quarks, they're essential for understanding how the universe works at its most basic level.
Exactly. And this paper we're looking at, it explores how these same techniques we've been talking about, like grooming and analyzing those observable classes,
Okay.
they can actually be used to identify these heavier particles too.
So it's like we're using the same detective skills to identify the VIP guests at our party, even if they're trying to keep a low profile.
Precisely. By studying the substructure of these jets, we can find clues about these heavier particles, even if we can't see them directly.
That's really incredible. But I got to ask, does it always work? I mean, do these techniques always work perfectly, or are there like challenges?
That's a great question. And it actually leads into one of the more, let's say, surprising findings of this paper. So remember how we were talking about that specific technique, KMOM2?
Yeah, the one that was giving us those like beautiful high curves on the graphs.
Exactly. Well, it turns out that same technique, it doesn't work quite as well at higher energies, especially when we're trying to identify those heavier particles.
Really? Why not? You'd think a technique that good would just like work across the board.
Well, it's kind of like, imagine you're using a magnifying glass to look for something in a giant field, right? The magnifying glass might be great for finding tiny details up close,
Yeah.
but it's not going to be very helpful when you're dealing with something much bigger and farther away.
Okay, so you're saying just like we need different tools for different tasks in everyday life, physicists need different techniques and algorithms for analyzing particle at different energy levels.
Exactly. And that's one of the, I think, really key takeaways from this paper. That optimizing these algorithms for specific energy levels, it's absolutely crucial if we really want to maximize accuracy and uncover those hidden patterns in the data.
So where does that leave us then? We've covered a lot of ground today, from messy particle parties to the standard model and those elusive W bosons and top quarks. What's the big takeaway message for our listeners?
I think the most important thing to remember is that, we're constantly pushing the boundaries of knowledge with this kind of research.
Mhm.
By studying these particle jets, we're not just looking at some like abstract data points on a graph.
Right.
We're actually piecing together the fundamental building blocks of the universe, and to me, that's incredibly exciting.
It really is mind-blowing. And, it kind of makes me wonder, what if we could build, like, the ultimate particle detector?
Hmm.
One that's not limited by today's technology? What kind of amazing discoveries might be waiting for us then?
Now you're asking the really big questions. Imagine a detector so powerful that it could capture every single particle produced in a collision. And not just its energy and momentum, but maybe even its entire history, where it came from, how it interacted with other particles, everything.
It'd be like having a time machine for the subatomic world, right?
Yeah.
We could rewind and see these collisions unfold in slow motion.
Exactly. What incredible details might we uncover? What new laws of physics might we discover? It's hard to even fathom the possibilities.
It really is. Well, this has been quite the deep dive, and I gotta say, jet substructure is way cooler than I thought it would be.
I'm glad you think so. It's truly a fascinating field with so much potential for, groundbreaking discoveries in the future.
A huge thank you to our expert for guiding us through this intricate world. And to all our listeners, thanks for joining us on this deep dive into the fascinating world of jet substructure. Until next time, keep those brains buzzing, and who knows, maybe one of you will be the one to design that ultimate particle detector and unlock the universe's deepest secrets. This is The Deep Dive. Signing off.